Hello, I am Rahul Baghel, Assistant Professor, Chhattisgarh Swami Vivekanand Technical University. Welcome you all to the course on Industrial Automation and Drive. Today, we begin with our 14th lecture on PLC Timer Programming Part 1. In the previous lectures, Swati Verma ma'am will cover the automation hierarchy, basics of PLCs, the binary concept, PLC programming rules, PLC programmings for basic logic gates. In this lecture, we are focusing the PLC timer. So let's start the timer in the industrial automation. First, start with the mechanical timing relays. Mechanical timing relays are essential component in industrial control system used to delay the opening or closing of contacts for circuit control. They function similarly to the control relays but include a timed delay in their operations. This relay provides time delay through two arrangements. First one is on delay and second one is off delay. On delay means delay when the relay coil is energized. Off delay means delay when the coil is de-energized. As you can see in the diagram also, the solid state timing relays, pneumatic timing relays and the plug-in timing relays are shown in the diagram. These are example of mechanical relays. Next, the on delay timer is sometimes referred to as a DOE, which stands for delay on energize. The time delay of contacts begin when the timer is switched on. It is two type, NOTC and NCTO. NOTC stands for normally open timed closed contacts and NCTO stands for normally closed timed open contacts. So let's start with the NOTC. As you can also see in the diagram also, you can see the switch is represented by S1 and the output is represented by the L1. And the same time you can also see the timing diagram for the operations. The operation of the circuit follows the following step. In the first step, with S1 initially open, TD coil is de-energized. So TD1 contacts are open and light L1 will be off. In the next step, when S1 is closed, TD coil is energized and the timing period starts. TD1 contacts are delayed from closing, so L1 remains off. After the 10-second time delay period has lapsed, TD1 contacts close and L1 is switched on. When S1 is open, TD coil is energized and TD1 contacts open instantly to switch L1 off. Next is NCTO. As I said, NCTO represent normally closed timed open contacts. You can also see in the diagram also. In this diagram also, switch is represented by S1 and output is represented by L1. The operation of the circuit follows the following step. In the first step, when S1 initially open, TD coil is de-energized, so TD1 contacts are closed and light L1 will be on. In the second step, when S1 is closed, TD coil is energized and the time period starts. TD1 contacts are delayed from opening, so L1 remain on. In the next step, after the 10-second time delay period has lapsed, TD1 contacts open and L1 is switched off. And the next step, when S1 is open, TD coil is de-energized and TD1 contacts close instantly to switch L1 on. Similarly, off delay timer, it is also two type, NOTO and NCTO. NOTO represent normally open timed opened contacts and NCTO normally closed timed closed contacts. First start with NOTO. You can also see in the diagram and the timing diagram is also seen. In the diagram, S1 is represented the switch and L1 is represented the outputs. The operation of the circuit follows the following steps. In this case also, when S1 is initially open, TD coil is de-energized, so TD1 contacts are open and light L1 will be off. When S1 is closed, TD coil is energized and TD1 contacts close instantly to switch light L1 on. In the next step, when S1 is closed, TD coil is de-energized and the timing period starts. After 10 seconds, time delay period has lapsed. TD1 contacts open to switch the lights off. Next is NCTC. You can also see in the figure NCTC, normally closed, time closed contacts. In this case also, input switch is represented by S1 and output switch is represented by L1. In the first step, the operation of the circuit is also shown in the timing diagram. In the first step, with S1 is initially open, TD coil is de-energized, so TD1 contacts are closed and light L1 will be on. And in the next step, when S1 is closed, TD coil is energized and TD contacts open instantly to switch light L1 off. In the next step, when S1 is open, TD coil is de-energized and the timing period starts. TD1 contacts are delayed from closing to L1 remaining off, and after the 10-second time delay period has lapsed, TD1 contacts close to switch on the light. Right? I guess you understand the procedure and the working of the mechanical relays, on delay and off delays. Next, we will start with the PLC timer instructions. PLC timer instructions that provide the same function as on delay and off delay mechanical and electronic timing relay provides. PLC timer offer several advantages over the mechanical and electronic timers. Those are, the first advantages are the entire timing function occurs inside the controller. Second one is, the second advantage is the time setting can be easily changed. Third advantage, the number of timer used in a circuit can be increased or decreased through the use of programming changes rather than wire changes. And the last advantage is when the timer accuracy and repeatability are extremely high because the time delays are generated in PLC processor. In general, there are three different PLC timers: on delay timer, off delay timer and retentive on delay timer. Before starting the programming, first we can understand the timer commands and the terms used in the programming. So I'll start with first is TON. TON represented timer on delay and it counts time based interval when the instruction is true. Second one is TOF. It represented timer of delay, counts time based interval when the instruction transition from true to false condition. Next is RTO, that is retentive timer on, counts time based interval when the instruction is true and retain the accumulated value when the instruction goes false or when the power cycle occurs. Next is RES, represent the reset. Reset retentive timers accumulated value to 0. With this, some other quantities are also associated with the timer instructions. They are, first one is time base. The time base of a timer refers to the unit of time a timer uses to measure an event. Depending on the PLC's manufacturer, the type of time base value can range from 1 millisecond to 1 second. Next one is preset value. The preset value of timer represents the time duration for timing circuit. Total timing interval is equals to preset value multiplied with the time base. For example, for a timer with a preset value of 100 and the time base of 0.1 second, the time duration is equals to the 100 multiplied by 0.01 second, that is 10 second. Next is accumulated value. The accumulated value of the timer represent the amount of time that has lapsed from the moment of the timing started. It keeps track of how many times the time base has occurred since the timer instructions was initiated. In the figure also you can see the timer, T on timer with the three values PR, TB and AC. PR represent the timer preset value and the TB is the time base of the timer and AC is represent the accumulated value and the timer address is represented by XSX for example. Next we can see the Allen Bradley SLC 500 timer file which is shown in figure is represented by T4:2 where T4 represent the timer file and 2 represent the timer element number and where the number is represented by 0 to 255 timer elements per file. In the similar way, T4:2/DN represent the done bit and the T4:TTs represent the timer timing bit and T4:2/EN represent the enable bit. So you can say that every timer has 3 bit, the done bit, enable bit and timer timing bit, as you can also see in the diagram also. Next, the control word use the following 3 control bits. As I already mentioned, enable bit, the enable bit is true whenever the timer instruction is true. When the timer instruction is false, the enable bit is false. Timer timing bit, TT, the timer timing bit is true whenever the accumulated value of the timer is changing, which means the timer is timing. When the timer is not timing, the accumulated value is not changing, so the timer timing bit is false. Next one is done bit. Done bit changes states whenever the accumulated value reaches the preset value. It states depends upon the type of timer being used. So let's start the first T on timer instructions. As you can see in the diagram also, one T on timer is connected with the input switch A. The address of input switch is represented by I:0/0 and the timer is represented by T4:2. So you can see in the diagram timer is equals to 2. Time base we can select 1 second. Preset value and accumulated value are represented by 0. In the same time you can also see the timing diagram. In the timing diagram you can see initially all the 3 values are zeros. Time period are 0, then TT period is also 0, right? But after the sometimes when the accumulator value is equals to the preset value, our done bit is high and the timer provides the output, right? So in the diagram also you can see, I'll explain the operation once again. The operation of the circuit, initially when the input is off, timer remains in the off state with the enable bit, done bit and the timer bit all turned off. So it represented by EN equals to 0, DN equals to 0 and TT equals to 0. At the same time when the input is turned on, timer enable bit is activated. So enable bit EN is equals to 1 and the timer start counting. However, TT bit has also become 1 but the done bit remains 0 state, right? When the timed output becomes true, sometimes whenever the timer rung becomes true, enable is equals to 1, TT is equals to 0 and done bit is equals to 1. Hence the timer is said to be have an on delay. The length of the time delay can be adjusted by changing the preset value. In addition, some PLCs allow the option of changing the time base or resolution of the timer. As the time base you can select becomes smaller, the accuracy of the timer increases. Let's take some example to understand the T on timer process. In the first example, suppose we have one input A and the three output B, C and D connected to the enable bit, timer bit and the done bit respectively. As you can see in the diagram also, the input switch is represented by I colon 0/0 and the timer is connected to the rung 1 and the timer address is represented by T4 colon 0. The preset value represented by 10 and the time base we are using 1 second. In the second rung, you can see the output B is connected to the T4 colon 0 enable, that is enable bit of timer, and the address of the output B is represented by O colon 0/0. In the similar way, you can see on the third rung, the output C is connected to the timer bit, that is TT bit of the timer, and the address of the output C is represented by O colon 0/1. And the last rung, you can see our output D is connected to the done bit and the address of the output D is represented by O colon 0/2. Right? So let's take the first case. Whenever switch A is 0, means switch A doesn't change their state, it remains their original state. As you can see in the diagram, switch A is represented normally open. That's why our timer doesn't get any type of input. That's why enable is equals to 0, done bit is equals to 0 and TT bit is equals to 0. Right? So all the three output generated by the timer is 0. So if all the three bits are 0, enable, timer and the done bit is 0, that's why all the three outputs connected to that bits are also 0. So in the first case, when A is off, all the outputs B, C, D is 0. In the next case, when we on the switch A, means A is equals to 1, in this case our switch changes their states from normally open to normally close. That's why you can also see in the diagram also, that's why the first rung our timer gets the supply, that's why enable bit is high. In the second rung you can see our T4 colon 0 enable is high, that's why that switch is also changes their state from normally open to normally close, and the output B is become high because output B is connected to the enable bit. As the timer function, when the timer gets the input, accumulator start counting, and when the accumulator start counting, our TT bit is also high. That's why you can also see in the figure the third rung TT bit is also high, T4 colon 0/TT is also high. That's why our output C is also high because output C is connected to the timer bit. Right? I guess this process is clear to you. I am again explaining. Initially our timer is off in the first case. In the second case, when I start the switch A, our timer gets the supply. That's why enable bit is high and our timer start counting from the 0. That's why TT bit is also high. So our output B and output C is connected to the enable bit and the TT bits. That's why these two outputs are also high. In the third case, when A is already on, when accumulator value is equals to the preset value. Right? In the third case, when the accumulator value is equals to the preset value, in this case done bit is high. That's why you can see in the diagram the last rung output D become high. But in this case you can also see our TT bit goes to 0 because in this case timer doesn't count further, it stop counting because accumulator is equals to the preset value. That's why TT become 0, that's why the output C become 0. Right? After analyzing these three cases, we can conclude that when input A is turned on, the final output D, which is connected to the done bit, will be activated after 10 seconds. This behavior indicates that the timer has an on delay because it introduces a delay before turning on the outputs. So let's take an example number 2. Suppose we have two switch, one for start and one for stop, and the three motors M1, M2 and M3. Our task is, when we press the start switch, M1 will on, after 10 seconds M2 will on, and after 10 seconds M3 will on. Means 20 seconds after pressing the start switch, all the three motors will turn on, and when I press the stop button, the all will turns off, means all the motor will stop. So let's see the solution. As you see in the programming, we can connect our all the three motors, motor 1, motor 2 and motor 3. Motor 1 is connected to the binary bit, motor 2 is connected to the first timer done bit, and motor 3 is connected to the second timer done bit. The start switch and the stop switch is also connected in the first rung. The address of start button is represented by I:0/0, and the stop switch is represented by I:0/1, right? So let's take first case, when start is off, means start is 0. In this case doesn't happen, means because start button is represented by normally open. So when start is normally open, our binary output becomes 0, and the binary output, you can see the binary output is connected to the motor 1, and the same binary output is connected to the first timer. So our first timer doesn't get any input, and our first motor is also doesn't get any inputs. So that's why the motor 1 is off. In the same way, timer it doesn't start counting, and the first timer done bit is connected to the motor 2. That's why motor 2 is also off. And the same way, that first timer done bit is connected to the second timer, that is T4:2, and that's why second timer is also doesn't start counting. That's why the done bit is also 0. That's why motor 3 is also off. So when the start is off, all the three motors are in the off state. Next, when I press the start button, our binary output become high. As you can see in the diagram also, our first rung, the output B3:0 is high. As you can see in the second rung and the third rung, the binary output address is provided to the input switches. So our motor 1 is high, and the same time first timer, that is T4:1, is also get the supply. So the enable bit is high, and the timer start counting from 0 to 10. Right? You can also see in the diagram, motor 1 is high as per the condition. When I press the start button, our motor is high, right? And the same time, our first timer start counting for 10 seconds. In this case, you can see the motor 2 and motor 3 remain in the off state, because motor 2 is connected to the first timer bit done bit, and the motor 3 is connected to the second timer done bit, right? Let's take the next case. When our first timer done bit is high, means first timer, the accumulator value is equals to the preset value. In this case, our first timer done bit is high, and the done bit is given to the input to the switches. That's why motor 2 become high, right? And the same time, this done bit is connected to the second timer input switches. That's why our second timer is also start counting, because it's get supplied, right? So the second timer is also start counting from 0 to 10 seconds. That's why you can see in this case, means after 10 seconds, my motor 1 is high and motor 2 is high, but motor 3 remains in the off state, because my second timer is counting states, right? Let's take the next case. Means after 20 seconds, you can see my second timer done bit is also high, because in the second timer case is also when the accumulator is equals to preset is initiated. That's why the done bit is high, and my motor 3 is connected to the second timer done bit, That's why my motor 3 is also high. So as per our task, when I press the start button, my motor 1 is high. After 10 seconds, motor 2 is high, and after 10 seconds, motor 3 is high, right? And the next case, when I press the stop button, my stop button is represented by normally close. It changes its state to normally close to normally open. That's why my binary output B3 colon 0 become 0. That's why if binary output becomes 0, that's why the motor 1 connected to the binary output will also become 0. And the same time, my timer 1 is also goes to 0 because it's also connected to the binary output. That's why timer is also 0. So the timer done bit has also become 0. And the same time, timer 2 is connected to the timer 1 done bit. So timer 2 is also become 0. That's why the motor 2 and motor 3 is also 0. So when I press the stop switch, all the three motors, motor 1, motor 2 and motor 3 goes in off state, right? As my process required, right? I think you understand the procedures and the programming part. For this, let's take another examples. Suppose we have a start switch as a green button and the stop switch as a red button. When we press the green button, the horn will sound for 20 seconds. After 20 seconds, the horn will stop and the motor will turn on. We have to prepare the logic for that. So let's take the first case. You can see in the diagram also the green button and red button. The address of the green button is represented by I colon 0 slash 0 and the red button is represented by I colon 0 slash 1, right? So when the green is off, at the previous case, similar to the previous case, when the start button is off or when the green button is off, my binary output has become 0. So binary is 0, that's why my timer T4 colon 0 doesn't get any supply, that's why timer is also 0. That's why the outputs connected to the done bit and the timer timing bit is also 0. So in the first case, when green is off, horn and motor are in the off state, right? In the second case, when I press the green button, as you can see in the diagram also, when I press the green button, my binary output become high. That's why the timer address, which is represented by T4 colon 0, is also high. So enable bit is high and my timer start counting. When the timer start counting, my TT bit is also high. That's why you can see in the diagram my horn is on because my horn is connected to the TT bit and the timer is counting till 20 because the preset value is 20. So for the 20 second, my horn will be on because of TT bit, right? After the when the accumulator is equals to preset value, means when the timer start counting and the accumulator is equals to preset value, means accumulator is 20 and the preset is 20, my done bit is also high. You can see in the diagram in the third case, my done bit is high. That's why my motor start counting, my motor is on, right? And you can also see in this case my TT bit becomes 0. That's why my horn is in off state, right? As I already mentioned, for the T-on timer, when the timer gets the supply, its enable bit is high and its TT bit is high, and the TT bit is high till the accumulator is equals to the preset, and after that when preset accumulator is equals to preset, my done bit will become high. So in this case also, after 20 seconds, my done bit will be on, so my motor will be on, right? So that's all for today's lecture. I'll just summarize this. In this lecture, we covered the mechanical timing relays, PLC timer instructions, and the T-on timer, and some example related to the T-on timer. I guess and I think you will learn the T-on timer programming. In the next session, we will explore more on the PLC timer programming. Thank you and happy learning.